Okay, so today we're going to talk about the average value of a function, and what you're going to notice today is actually the average value of a function is equivalent to the mean value theorem when we talked about that in the first semester. So the average value of a function has to do with kind of, in some sense, the mean value theorem for integrals. Okay, and we'll eventually get to that. So before we do any of that, let's kind of define what the average value of a function is. So we're going to say, look, consider the continuous function from A to B. So kind of like imagine if we have a function that's continuous that goes from A to B. So then the question is, well, what is our goal, or what are we trying to do here when we're talking about finding the average value of a function? So our goal now becomes, so our goal is to find the average value this function takes on from A to B. Okay, with that said, it's kind of like, okay, well, what does this mean? You know, we're saying our goal is to find the average value that this guy takes on from A to B. So in other words, here's what we're saying. That is, we want to find the average y values, so that should be an L, this function takes on from A to B. So in other words, what we're saying is, look, I want to take all the y values that this function takes on from A to B, and I want to average them out. And then the average of that will be the average value of this function from A to B. So here's what we know. For the finite case, that's not difficult. In fact, we're pretty good at doing that. So we could say, look, the average value is easy to find for a finite number of y values, right? And as always, how do we find the average value? We're saying this can be found as y sub 1 plus y sub 2 plus all the way to y sub n divided by n. So you're basically doing what? You're grabbing all of your y values, you're adding them up, and then you divide by how many y values you have. And so let's actually call this equation number 1 because we're going to reference this in a minute. Okay, so that's not difficult to do, okay? But here's the issue we have. So the issue we have is that the function defined above has an infinite number of y values from A to B, right? And so think of it this way. For the finite case, we said we're okay with it. But the problem is, if I come back to this graph right here, if I were to tell you, hey, look, from A to B, how many points are there? And the answer should be there are infinitely many points. And if there are infinitely many points, that means there are infinitely many y values. So then the question becomes, well, then how do I find the average value of a function when it has infinitely many y values? And so you could already see where we're kind of headed with this, because in calculus, everything we've done, especially this second semester, we've said we want to work for the case where we're dealing with infinitely many um, partitions of whatever it may be, whether it's rectangles or areas and so on. So what we're going to do is we're going to say, okay, so now we want to extend the finite idea, which is equation 1, to infinity. So we're going to grab this and send it to infinity. Okay, so what we're saying now is, okay, so let's go to what we had. So we're still going to use the equation 1. But now what we're going to do is we're going to say, okay, look, if we divide the interval from A to B into n equal subintervals, what do we get? Well, we have delta x equals to b minus a over n. So if you notice, I'm grabbing this and I'm breaking it up into an equal number of subintervals, okay? And they're evenly spaced out. So, and we could say, look, y sub 1, y sub 2, all the way to y sub n are equally expressed as f of x sub 1 star, f of x sub 2 star, all the way to f of x sub n star. As you notice, I mean, these are still y values, right? So I'm saying instead of calling it y1, y2, all the way to yn, I could call it f of x sub 1, x sub 2, all the way to x sub n star. Now, if you remember the star, these are my sample points. So since I'm breaking this up into subintervals, am I using the left endpoints, right endpoints, midpoints, whatever it may be that I need to get that guy? Okay, so here's what we could say now. So equation 1 becomes, so if we go back to equation 1, we could kind of update it. What does that look like? It'll be f of x sub 1 star plus f of x sub 2 star plus all the way to f of x sub n star. All of this divided by b minus a over delta x. Okay, and so how did I get this? Well, if you grab this and solve for n, because if you remember, we were dividing by n, and if you grab this and solve it for n, you get that, b minus a divided by delta x. So now if I simplify this and say, look, this times the reciprocal of that, that gives me 1 over b minus a f of x sub 1 star delta x plus f of x sub 2 star delta x plus all the way to f of x sub n star delta x. Okay, and then what we could say is, well, we could simplify some more because all of these have a delta x. So if I factor out a delta x, I'm left with f of x sub 1 star plus f of x sub 2 star all the way to f of x sub n star times delta x, which then this becomes 1 over b minus a. This is just a summation, isn't it? So I could write that as the summation from I equals 1 to n of f of x sub I star times delta x, which this should look familiar to you. Okay, so basically we can say, look, what is this? This is for the finite case, but what is it that we have? How many y values are we going to have? We're going to have infinitely many, so we're going to send n to infinity. So we're going to say, as we send n to infinity, we get 1 over b minus a limit as n goes to infinity, summation I equals 1 to n of f of x sub I star times delta x, which hopefully this looks familiar to you. I hope you haven't forgotten this because it wasn't too long ago we talked about this, but this is the definition of a definite integral. So we know how to use the definition, but we also know the shortcut. So this whole thing is equivalent to what? 1 over b minus a, integral from a to b of f of x dx. So this is my average value function. So, and it's for the infinite case, which is what we have. So this actually describes the average y value a function takes on from a to b, okay? So here's what we could say. To summarize this, we could say, so the average value of a function f on the interval from a to b is f average equals 1 over b minus a times the integral from a to b f of x dx. And there you have it. Okay, so that's my average value of a function. So hopefully you understand what this is saying. This is just telling you that on average, a function from a to b, as long as it's continuous, takes on this y value. So when you evaluate this, that's what your y value is. Okay, so let's look at our first example, and then we'll move on to the mean value theorem for integrals, and that'll basically do it. So for example 1, we're going to say find the average value of f of x equals to 1 plus x squared on the interval from negative 1 to 2. Okay, and so what do I know? Since 1 plus x squared is continuous everywhere, this definitely doesn't have an average value. So what is that going to be? F average equals to the 1 over 2 minus negative 1 integral from negative 1 to 2 of 1 plus x squared dx. So if we go through this, what does this become? 1 over 3 times, what's the antiderivative of that? It's just x plus 1/3 x cubed from negative 1 to 2. And we just plug in the upper limit, which is 2 plus 8/3. And then we'll say minus 1, or it'll be minus negative 1 minus 1/3, which equals to 1/3 times 2 plus 8/3. What is that? That's 14/3. And then minus 1 minus 1/3, that's negative 4/3 with a negative. It'll be plus 4/3, which becomes 1/3 times 18 over 3. And this becomes just 2. Okay, so what are we saying? That this function from negative 1 to 2, if I were to grab all of its y values it takes on and if I were to average it out, it would be an average of 2. Okay, so what we're saying, the y values of this function are on average, they give a y value of 2. Okay, so now with that said, let's talk about the mean value theorem of or for integrals. So before we go on to the mean value theorem for integrals, if you remember the mean value theorem, what did the mean value theorem in semester 1 tell us? It said, look, if you have a continuous function, let's say, let me just draw a picture here. You don't have to put this in your notes, but I just want to draw a picture just so you see it. If I give you a function that's continuous from a to b and is differentiable, then what are we guaranteed? There's somewhere on this curve, call it C, where the instantaneous rate of change is the same thing as the average rate of change. And so we have something similar. See, this is saying, in other words, it's saying the slope of the secant or the rate of change from a to b is the same thing as the derivative of this guy at c. So we have the same thing for integrals. And as you could see, it's going to involve our average value. Okay, so here's what the mean value theorem of integrals says, and I'll show you a picture, and I'll give you a picture as to what this means, and then that should pretty much clarify things here. So we would say if f is continuous on the closed interval from a to b, then there exists a number c in the interval from a to b, and it's a closed interval, such that f of c equals to 1 over b minus a integral from a to b of f of x dx, which, by the way, this is just literally your f average. Okay, now another way of putting this, which kind of visually makes more sense, or this is equivalent to what? The integral from a to b of f of x dx is equal to f of c times b minus a. So if you look at these two, they're literally the same thing, because what did I do from here to here? If you kind of observe carefully, what I did to get from here to here, I just literally multiply both sides by b minus a. So if you multiply both sides by b minus a, you get just this integral, and then you get f of c times b minus a. Okay, so they mean the same thing. Okay, so what does this mean visually? So to kind of give you a picture that describes this, so a picture describing this, here's how it looks. And I'm going to use this idea because this is easier to kind of show us what's going on. So we already know that the integral from a to b of f of x dx, that's just literally the area under the curve of f from a to b. So if I were to draw a function, all right, and so let's just say that this function looks like that from a to b. And of course, it's continuous. And so what does this mean? That's just the area under the curve from a to b of f of x. So what we're saying is that this region, which is described by the integral from a to b of f of x dx. Okay, so that's what this is. Now, what this is saying is, look, you could find somewhere in this interval, and it could also be at the endpoints, but there's the location here, which you call it C, where when you go up to the curve, which notice how this y value would be f of c. Now look, what's f of c times b minus a? Well, b minus a is that length, f of c is that height, so if I were to draw this rectangle here, so what do you notice? B minus a times f of c is the area of this rectangle. So what we're saying is, now let me shade it the other way, the area of this rectangle is represented by, so let me actually do this. Let me box this just so we don't get confused. So the lines that are going diagonally this way, that represents this area, and then the box, I'll put where the diagonals are going this way, that represents the area of what? F of c times b minus a. So what are we claiming here? This is saying that the area of the rectangle, which is this right here, is equivalent to the area under the curve of f of x. So as you could see, hopefully you see the similarities with this and the mean value theorem for derivatives. This is just a mean value theorem for integrals, which says, look, you could find a place on your curve where when you create your rectangle and you find the area of that rectangle, that will be equivalent to the area under the curve. Okay, now there could be more than one place, but we know that we're guaranteed to have at least one place. Okay, so hopefully that makes sense. If not, make sure to ask me during class and I'll kind of clarify it. So let's move on to our second example, and that'll basically finish up this section. So we could say, find the number c in the interval from -1 to 2 such that the integral from a to b of f of x dx equals to f of c times b minus a. So basically they're asking us to find that number c, where if I were to find the area of the rectangle, it'll be the same thing as the area under the curve. So the good news is and basically I haven't given you the function, which you'd be kind of stuck um, for f of x equals to 1 plus x squared. So the function that I'm giving you is the same function from example 1, just because I don't want to waste our time kind of doing more than we need to. So here's what we know. We need to find what? The integral from -1 to 2 of 1 plus x squared dx, which basically becomes what? X plus 1/3 x cubed from -1 to 2, and then that becomes 2 plus 8/3 minus -1 minus 1/3, which we already did all of this, didn't we? And when we simplified this, for example 1, what do we get? We actually ended up getting, where did I write this down? Oh, well, let's just finish it up. So it'll be 14/3 plus 4/3, which is 18/3, and that is 6. Okay, so that we have. So then what we need to find is we need to find c. Okay, so here's what happens. So this integral, or what we're claiming is we need the integral from -1 to 2 of 1 plus x squared dx. This has to equal to f of c times b minus a, which is 2 minus -1. So this we just found. So what do we know? 6 equals 2. That becomes 3f of c, which this implies that f of c equals to 2. Okay, which is practically what we did in example 1. So I kind of did all this work for no reason, but I just kind of want to show you what it was. So we got f of c equals to 2. Now remember, we haven't found c. We found the y value at c. Now what's the question saying? Find the number c. So what do I know? When I plug in c into f, the output should be 2. So if I grab f, which is this guy right here, and I replace it with 2, so what am I claiming? If I replace x with c and f of x becomes 2, I get what? 2 equals to 1 plus c squared, right? Because all I did is I grabbed this and I replaced f with 2 and I replaced x with c. And now I could solve for c. And when I solve for c, what do I get? I get 1 equals to c squared, which implies c equals to plus or minus 1. So then I just need to make sure that these values that I got both are in my interval. And when I look at my interval goes from -1 to 2. And both -1 and 1 are in my interval. So this implies that there are 2 locations. So there are 2 locations that work. One is when c equals -1, and the other one is when c equals to 1. So basically, if you were to go create your rectangle at 1 and -1, you would see that the y value would be 2. So you make your rectangle. The area under the rectangle would be the same as the area under the curve of this guy. Okay, and so that would basically give us exactly what we're looking for. So this basically is what the average value of a function is about. So if you look at the mean value theorem for integrals, it is literally using the same idea as the average value function. Okay, so now we're pretty much done with this section. Just make sure to ask questions if you have any, and I'll be more than happy to answer them.